Okay, so shall we start? So I will be doing weeks 9 and 10, and Manoj will do weeks 11 and 12. Okay, so that's the plan today. And for the first 8 weeks, you anyway have the old revision sessions, right? So the quiz 1, quiz 2 revision sessions. So you can refer to that. Now, what I'll do is I'll just go over the document which I had shared. I have cut down all the text and I only have important content from them, right? Say equations or something that's important to remember. Okay, so that one, and then I have added 2 more topics. So the skip-gram I didn't have in the document, and LSTM. So I'll go over that also very quickly. So I'll be going over these things quite fast because exam is in 2 days, right? So I'm hoping you know all of this. This is just a refresher. Okay, so yeah, so this is where we are now. We start with the corpus. Okay, so there is always, we assume that some corpus is given to us. It's a set of sentences, and what you do first is you build a vocabulary out of it. So you leave out all the duplicates. So for example, if some word occurs twice, you only retain one of them, right? And you build a vocabulary. Basically, you convert this into a set of words. That's your vocabulary. Now here the vocabulary is in ascending order, but that's not really important. It's just that it should be a set. Okay, so what you are interested in is getting a representation for the words, and that representation, the naive representation that you can think of is one-hot encoding, where for every word in the vocabulary, if there are 10 words, then you'll have 10 vectors. So there will be 1 in the position where the word occurs and 0 everywhere else, right? This is a typical one-hot encoding scheme for encoding words, representing words as vectors. Okay, but this suffers from many problems you already know. So one is that the
V is a set, sir.
Yeah, V is a set. Yeah, so it suffers from the some of these problems, right? The dot product is 0, and the distance between any 2 vectors is the same, right? And these are all not very conducive for word representation. So what we do is we go towards better embeddings which are dense. Okay, so the idea is we are trying to learn dense embeddings which take up fewer dimensions, but then each component of a vector can be a real number, right? So here they're all either 1 or 0, and the length of the vector or the number of dimensions is as many words there are in the vocabulary, and that's too many. So vocabulary sizes can go to things like 10,000, 50,000, right? So it can be as big as 50,000. We can't afford to have that big a vector for every word, right? So what we do is we try to look at dense embeddings, and that is where we have 2 principles that I always want you to remember, right? So a word is known by the company it keeps. So the context is very important, and words that occur in similar contexts, they are going to have similar meanings, right? So this is a very important thing to keep in mind for all future tasks that we are going to do with words. Okay, so this will be the guiding principle for us to learn these embeddings, right? So what else should we know about word embeddings? There's this idea called cosine similarity, which is stated in the lectures, but we never explicitly give the formula. So what is that? It's the dot product between 2 words, 2 word embeddings or 2 words. So whenever I say word embedding, think of a vector. Okay, so 2 vectors, you take the dot product, but the dot product can range from negative infinity to infinity. So what you do is you normalize them with the norms of the 2 vectors, right? That's not the only reason. The other reason is that if you okay, I think that's a good enough reason. Okay, so the cosine similarity will now range from -1 to 1. Okay, so the closer the cosine similarity is to 1, the more similar are the words. That's the intuition. Okay, and the closer the cosine similarity is to 0, the more orthogonal are going to be these 2 word embeddings, and the less similar they are. Okay, that's the idea. Or -1 means they are like totally dissimilar. Okay, so that is the cosine similarity. Now that's for a general word embedding. So there are different ways of learning word embeddings. We are going to look at 3 techniques. One is using co-occurrence matrices. and using this singular value decomposition to extract word embeddings. That is one. The second one will be continuous bag of words. Third one will be skip-gram with negative sampling. Okay, so these are the three important ones that you need to know. So what's the co-occurrence matrix? So you basically look at words and windows surrounding that word. Okay, so what is a window? So if the word is gold, right? And if you look at a window of size 2, then you look at 2 words to the left and 2 words to the right. So that is what is called a context window. Now, so how do you build the co-occurrence matrix? Once again, the same process you follow. You have a corpus. For example, if this is the corpus, then you build the vocabulary out of that corpus, and then you get the individual co-occurrence counts, right? So how do you read the co-occurrence counts? The rows are the target words. You call them the target word, and the columns are the context word. So you ask the question, for a 2-word context window of this, how many times does the word good occur in that context? So for example, if you look at this, so this is a 1 word. So this is a 1-word context window, meaning you only look at the left and right word. So for this, you have good occurring exactly once in its context, right? Therefore, this entry will be 1. Okay, this is how you build a co-occurrence matrix. In this case, for a single context window, okay, single word context window. But then you can do slightly better. What you do is you take help of the notion of mutual information from information theory. Okay, this comes from information theory. So what does this tell you? So this is called the point-wise mutual information between a pair of words. So the word and the context. Okay, so what is this? This is a ratio, and each of these, the numerator and the denominator, both of them represent something meaningful. So the numerator tells you how likely it is that the word and context appear together, right? So how likely is it that W and C occur together in a sentence? The denominator tells you how likely it is that W and C, if you pick 2 words at random, the denominator tells you how probable that event is of W and C occurring together. Okay, so denominator represents random chance. Okay, it's a chance event. If you pick 2 words at random from the vocabulary, what is the probability that you see W and C? Okay, so you can treat them as independent events, right? So picking 2 words, you pick them independently, therefore you multiply the probability. Whereas this is something different, right? So this is the co-occurrence probability. And what is your PMI? PMI is comparing these two things, right? How likely it is that the words co-occur compared to random chance. So higher the PMI, the more likely it is that W and C form a word context pair. So that's the idea. Now, how do you estimate the PMI? You use,
Sir, can I ask a question? Sir, can I just scroll up a little bit? So there we have 4 sentences, right?
Yeah.
So while getting the context window, we have to separate each sentence one by one, or should I take, like for example, in first sentence, is there, right? Is
Yeah, you keep it as, so see, actually this is, it's more of a, depends on use case to use case. So you can keep sentences as separate sentences and then look at and then compute the co-occurrence count. Sometimes what is done is the entire corpus is concatenated so that it's one long sentence. But for our course, you can keep them as separate sentences. So good, and the good that is here is not a neighboring word for is.
okay. So we have to add the start and the stop. That
Yeah, you can. Yeah, you can think of this as a start marker is there here, and end of
okay.
sentence marker is here.
Go and enter. Okay, that we have. Okay. Use.
Yeah, so that's the PMI. Now, how do you estimate these probabilities? You use counts, right? This is how often do you look at the corpus and you count W comma C. So for example, here it will be, so is and this, right? So if W is and context is this, then count of W comma C would be 3. Okay, and N is the total number of words in the corpus. So N is the words in the corpus. Okay, and then you can just compute these values. So count of W is how many times W occurs, so on and so forth. Okay. Now, if you take this ratio, you will end up with this formula. So it's easier to remember this formula and these three, right? So that way you can derive the PMI quite easily. So
So
this
N,
is,
sir, N is not unique words, right?
no, it is the total number of words in the corpus.
Vocabulary size.
No, that will be the unique number of unique words, right? So it's
Oh,
the,
okay.
here it is 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13,
Okay, sir.
right?
So
So
if
yeah,
n is given in a question, should we take the n in the question or number of words in the corpus?
yeah, you can take the N in the question. I was also a bit kind of surprised by that in the graded assignment, right? So for some reason,
They
N was
gave
given
9
at
and
some
7
point.
was 10. Yeah.
Yeah. So for, yeah, you can assume that N will be the, it will not be given and it will be the total. You have to compute the total number of words in the corpus.
Okay.
Okay. So that is,
So during counting, should I remove the duplicates?
no, that will mean you will just, that means N will just be the vocabulary size, right? No, you have to count the duplicates also.
Okay.
Sir, is it always log to the base 2?
Yeah, so this is coming from information theory, right? If you remember entropy, so entropy in MLT we studied, right? So that was also log to the base 2. So this is mutual information.
So binary relationship, that one only we are taking.
Sorry?
We are taking two items together. That's why we are giving two base, right?
Not in that sense. It's more of the base 2 comes because whenever I don't know information theory much, but there you deal in terms of bits, right? So information you process them in terms of bits. So
binary 0 and 1.
Yeah, entropy itself is, you call it these many bits of information you process, things like that. So therefore, it doesn't matter. Strictly speaking, you can use any base. It's just a scaling factor, right? If I replace this by E, all that it would do is it will scale the PMI by some value. That's all. But let's just use 2 itself. Okay. Yeah. So once you know the PMI, what you can do is the PMI can be negative. So what you end up doing is you replace it with the positive pointwise mutual information. It's just like ReLU-like thing, right? So it's max of 0, PMI. Okay. So now what do you do next? You, given a corpus and the vocabulary, you construct this PPMI matrix. Okay. So this is a PPMI, the PPMI matrix, or rather the co-occurrence matrix with PPMI values, right? So
every element of this matrix represent PPMI value, right?
yeah, PPMI value. Yeah, every element will be one such value.
Okay.
Okay, so that is how you construct X. So it will be a vocabulary cross vocabulary matrix. Okay, so in this case, in this example, it will be 4 cross 4. Okay, so this is a raw co-occurrence matrix, right? So with just the raw counts, word context counts. Now, but then we usually work with the PPMI one, right? So once you have PPMI, what do? You take the help of SVD. SVD is a matrix factorization technique, right? So it allows you to extract a low rank approximation of the input matrix. Okay, so and that's what we'll do. So if you do the SVD, if you perform the SVD on X, you will get 3 matrices. So the left singular vectors will be in U, sigma will be the singular values, and it will be a diagonal matrix. We will have the right singular vectors. Okay. So what you do is you only retain the first k columns. If you want a low rank approximation of say a rank D. Okay. What you do is you retain only D columns. So for U hat, you will have first D columns. For sigma, it will be a D cross D, first D cross D diagonal matrix. It will have D singular values, and V hat, you will retain the first D column. So if you multiply U hat, sigma hat, V hat, you will notice that X hat is still V cross V. Okay, so that you have to keep in mind. So X hat still is V cross V, but then the intermediate matrices are now of lesser rank. Okay. Now, how do you, all this is done so that you can extract word and context matrices, this is what you want finally. Okay, so can say everyone mute. I'm getting some noise in the same. Oh, so what is the word matrix? It's just you take this first two, right? You had sigma hat, and we had whatever remains is the context embeddings, right? So how should you understand W? W is this matrix where every column, sorry, every row represents word embeddings, right? So I'll just write that down. Every row of W corresponds to a word embedding. Okay. So with shape RD, so D cross 1. Okay, so it's a D-dimensional word embedding. So D may be typically values like 100 or 150. Okay, and likewise, every column of the context matrix every row of the context matrix will be a context embedding. Okay, so this is how you learn word embeddings with the help of SVD and co-occurrence counts. That is one thing. So this check is there in the lectures. I'm not going over it. It's just to show that this W that we obtain makes sense. You tie it to pairwise dot products between words. So you are kind of retaining the pairwise dot products. That's what this whole derivation means. Okay, so that is SVD. Now CBOW, that's the next one. Okay, so what is CBOW? It is continuous bag of words. It uses two assumptions. One is that you are treating your corpus as a, or your sentence rather, as a bag of words. Okay, meaning the order doesn't matter. So you are not really interested in what word follows what. The only thing you care about is which word is in my context and which word is not. Okay, so that is one assumption. It's called the bag of words assumption. The other one is that the word embeddings are going to be continuous. So they are going to be in RD, okay, rather than a discrete space like one hot vectors, right? So those are the two assumptions. So in CBOW, what is the model? You have your context window and you are kind of filling in the blanks. So CBOW is a typical fill in the blanks assignment given to a machine.
Excuse me, sir.
Yeah.
Excuse me, sir. You told that it is continuous here, no?
Yeah.
Whether does that mean that some probability?
No, that doesn't have to do with the probability. It has more to do with the vectors being represented as vectors in RD. So RD is a continuous space. Right? RD as
actually every word will have individually one vector, isn't it?
Yeah, but that vector. So what is a? So where does that vector live? It lives in RD, right? Let's say R3. So R3 means, so the 3 is kind of discrete, but that is not what you're referring to. R3 means every component can take any real value, right? So the entire, so R3 means the entire 3-dimensional space, any point in that space can represent a word vector. In that sense, it's continuous.
Even then, we will have to write it like this some elements, isn't it?
Correct, but what are those elements? See, how are you representing one hot vector? So you are representing one hot vector as discrete entities, right? So 1 0 0 0 1 0.
Yeah.
That is a word vector in R3, for example, can be 0.1 minus 0.5, 1.5. So that's where the
only that one, not real integers, but also real numbers.
Yeah, that's the continuity, right? The whole idea of continuity comes from working with real numbers, right? So
okay. Thank you.
Okay, so you are filling in the blanks for CBOW. So you are filling only one blank. So in Skip-gram, we will flip this and we'll kind of post it as filling in many blanks. But in CBOW, it's many context words together and just one target word in the middle. So in our course, what we are doing is we are simplifying things a lot. We are only going to look at one context word, which is the left context word, right? So this is like left, whatever is there on the left of the word, left of the target word, and then you have to predict the next word. Okay, so that's the idea here. So what are the embeddings? To begin with, embeddings are random matrices or matrices with random values. So note the shift here. Here every column is a word embedding. Okay, in SVD, every row was a word embedding. Here every column is a word embedding, and there are two matrices, one for the target words and one for the context words. Okay. So what is the model? Model is actually very simple. If you pass two vectors, one is a word target word vector, another context word vector, you just take the dot product to measure similarity. But then since you are interested in prediction, you need a probability distribution over the entire vocabulary. So therefore you take softmax. Okay. Now this is the idea. The model is as simple as this. So this is nothing but y hat evaluated at the target word W. Okay, so notice that the context is going to remain fixed, and you are going to, the summation is over all words in the vocabulary. Okay, so the W that you use here should be the word embedding, target word embedding, and not the context word embedding. Okay, likewise for W here. C, however, will come from the C matrix. Okay, so example is
Context will remain same that you are saying.
while predicting the probability of a target word, the context is going to remain the same, right? You are comparing so for example, if tree dog is T, so this tree will be the context. Okay, so the tree vector will come from the context matrix. Dog is the target word. Okay, so that is going to come from the word matrix, the W matrix, and so are all the other W's here, right? So any W that you see here has to be drawn from the word matrix, right? Because you are looking at potential words after tree. You're looking at potential target words after the context tree. So all these W vectors have to come from W, right? And only the context vector that will come from context, and that will remain fixed because there's only one context right here. Okay, that's the model. So now what is the setup? Your typical ML setup. So the data is going to be some large corpus, and you're going to learn in a self-supervised manner, meaning the labels are going to be there in the corpus itself. So the next word, given the current word, right? So the next word is the label. So model we have just described. It's a simple softmax over dot products between word and context vectors. That's the model. The loss is cross entropy, and the optimizer you can use SGD, right? So how will training work? So you initialize the word and context matrices randomly, then you run SGD. So I'm just giving you one sample. So if there is a context followed by a word, then the pair. Okay, so you can call it WC pair or CW pair. Where I hope you get the idea, right? So I'll used to calling it WC pair. So I'll just okay. So the context first and then the word. So how do you define the prediction? P of W given C, we have already seen this. Now the loss function is negative log of the predicted value y hat, and the gradient of the loss. So you can calculate the gradient of the loss with respect to W and C. Okay, and you have to ideally update both these values. But in the lectures, we have only seen how to do this for W. So we'll stick to that. So how do you update the word embeddings for the target word is all that we have seen so far, and we'll stick to that. Okay. So WT. So I hope you understand what WT means, right? WT is the word embedding corresponding to W, target word W, at time step T. Okay. WT plus 1 is at time step T plus 1. So how do you update the word embedding? You add the learning rate times the context vector and 1 minus the predicted probability of W being the target word. Okay. So if interpretation, I think you already know. So if this predicted probability is already close to 1, this term will essentially be 0, right? So if y hat is close to 1, what does it mean? It means that you're already predicting the target word correctly. So you don't need to change the target embedding that much. Okay. However, if y hat is, let's say, close to 0, that means that you are doing a bad job of predicting the target word. So what do? You move the current embedding close to the target word C, okay, by adding eta C into 1 minus y hat. So that's the idea. So the idea is, if two words occur close to each other in a corpus, their word vector should also be close to each other in the embedding space. That's the idea. Okay, and that's what the whole process tries to do. Okay, so that's CBOW. So Skip-gram, we'll only look at negative sampling. Okay, the rest of them are slightly hard, so we'll only focus on negative sampling. So what is happening here is you have one target word. It's like filling many blanks. So you have to, ideally what you should do is you have to predict the context words on both sides, right? So with the context window of size 2. But then this is kind of a hard problem. You have to think about, if you think about it, you have to do a softmax here, 4 softmax function evaluations need to happen. So what you end up doing is something simpler. You have a target word W, and then you divide the problem or the data into 2 parts, right? So you have to predict if a given word is in the context of the target word or not. So therefore, you end up with positive samples where W comma C is a word context pair. Okay, and then what you do is you sample randomly from the corpus. For each positive sample, you sample, let's say, k negative words, right? Negative words meaning what? Words which are not in the context of your target word. Okay, so I just maybe repeat this. So you have a target word W, and then you have 4 context words here, right? So each one will contribute to one positive sample. So let's take only one such sample, maybe say target word and context word 2. That is what I'm calling W comma C. And then what you do is you sample words from the corpus at random, and let's say you come up with k words which are not in the context of the target word. So you're going to call them negative samples, right? So your goal now is to train a model that increases or pushes the probability of a word context pair close to 1 and pushes the probability of a negative pair, right? A word and non-context pair close to 0. That's what you wish to do. Okay. So how do you do this? The model is actually very simple. So you just rely on the dot product again for comparing the similarity between word vectors. And since you are interested in binary classification task, you use sigmoid. So it's like you W and C go in, and this is the probability that they are a word context pair. Okay, so that is just sigma of W transpose C, and you just expand the sigmoid. The probability of them not being a word context pair, that will be what? 1 minus sigma of W transpose C, and that turns out to be sigma of minus W transpose Ci. So remember, C1 to Ck are all negative non-context words. Okay, so what is the loss? The loss is nothing but the negative log likelihood. So you can maximize the likelihood, or you can minimize the negative log likelihood. So the negative log likelihood will look like this. So minus log sigma of W transpose C. This is for the positive pair. This is sum over k negative pairs, right? And notice that this is a minus sign sticking here. That's because you are pushing, you want to maximize this, right? You want to maximize the negative pair, the probability of a negative pair is probably, what am I saying? You want to maximize the negative pair having a probability of 0. Okay, that's just fumbled that. Okay, did you get this part? How we obtained this whole equation?
Sir, if possible, can you make a small example how to do this?
Example.
Small example, small sentence, something.
So consider 4 or 5 words here, right? You can think of your own example. So this is some target word, and there is some other word here, right? So this together will make a positive pair. Can you imagine that?
Yes.
And then this along with some other word which are not these 4 words will form a negative pair. That's all.
Sir, this negative sample, where we are taking it from this V only, or it is from somewhere else?
Sorry?
No, we are, as you have told, that negative words, where we are taking it from the same V, same V vector, or it is from somewhere outside?
Where are we taking the negative words from? We are taking them from the corpus.
From the?
Corpus. The
that means inside that V only, no? If there are 25, for a small example, if there are 25 words, if you take one word and one context word, any other word can be negative sample, isn't it?
not any other word. So if you are sampling a negative word, you have to make sure that they are not these 5 words.
Within the window. They are not within the window.
Yeah, so you should make sure that it's not a context word itself. Otherwise, there's no point of sampling a negative word, right? So
context means when we take a one word window, left and right, isn't it? That is the context.
No, here it's a 2-word window. These 4 words make up the context.
In a 2-word window, 4 words will come. Okay. Yes. Okay.
Yeah, so the negative word
sometimes
is...
it may not be, if it is at the end of the sentence only, sometimes 3 only will be there, or 2, isn't it?
No, that you can kind of get around that by adding appropriate start of sentence and end of sentence markers. So that's a corner case. Let's not worry about that here. Let's only focus on the very essence of what this method is all about, right? So there are implementation details. For example, we didn't mention the thing that I mentioned now, right? We haven't discussed that in great detail, right? What happens if you sample a word at random and it is one of the context words? So that would mean a collision, and you have to avoid such collisions from happening. So you have to resample again if you end up with a context word itself. So there are some peculiarities that you have to deal with. For now, let's get around that, okay?
Okay.
The basic idea is clear, right? What is happening?
Yes.
Sir, when it comes to choosing the number of negative samples, is it something hyper parameter or some? It's up to us.
Yeah, you sample from the vocabulary, but so there is a hyper parameter governing it. So there is something called unigram frequency. So unigram is nothing but the frequencies of individual words, right? So you look at your vocabulary. If there are 4 words in the vocabulary, each word will occur with certain frequency, right, in your corpus. So you are going to sample based on that unigram frequency, but it's not just that unigram frequency. So there might be extremely rare words which have like very low probability. So you want to have some way of boosting those probabilities. So this is why if you look at the lecture slides, there is a parameter that is there. It's not just the unigram frequency, but there is something raised to power alpha or something. I don't remember what sir uses. So you sample using that frequency distribution.
Okay.
So that is a hyperparameter. That alpha or whatever, that is a hyperparameter. But other hyperparameter is the number of negative samples. So should you sample? So in this, what should be the value of k? Should it be 5 words? Should it be 10 negative samples? So all that comes into play. Okay. So for each W, so for example, if you consider two word context window, right? Each of these will make up one W, C pair. Okay. So there are 4 positive samples that will come from this W, C, so on and so forth, right? So I hope you get that. There are 4 positive pairs that will come from this. For each positive pair, you are going to sample k negative pairs. So the W is fixed so once you have a positive sample, you keep the W fixed, the target word fixed, and then you sample from your unigram frequency distribution k times. You pick up k words. If some of these words happen to be context words, then you discard and you resample. Okay, you do that until you end up with k words which are not context words. they make up your negative sample. So you do this for every positive sample, and then you build up your data set, right? Your data set will therefore have, let's say, there are 20 positive samples, it'll have maybe 20 into 5 negative samples. Okay, so what would that be? 120 samples in total. And then you train this model. Is that fine?
Yes,
Okay.
sir.
So here are we maximizing the negative samples also?
We are maximizing the probability of the negative samples. Sorry, again I'm making that mistake. So we are pushing the probability of negative samples. Sorry, I'll write it down. So what we want to do is we want negative samples to have 0 probability, right? That's what we desire. And we want positive samples to have probability. This is what we desire, okay? So you
So
can treat.
then why sign is same the negative sign in the loss function?
The negative sign, but then this minus is there, right? You are missing this minus. See, you want to maximize 2 things. You want to maximize this probability. This is a positive pair. You want to maximize this probability. Okay, it's a negative pair. So this is clear, right? So you want to maximize this value and this value. So you want to maximize 2 things. Therefore, there's the same sign. But what you have to note here is this is a W transpose C and this is a minus W transpose C. So whenever you see a minus sign inside sigmoid of something, it is the inverse probability, right? 1 minus sigma of Z. So remember that. So recall what sigma of Z is, or minus Z is 1 minus sigma of Z. That's what we have used here, right? For one sample, so for one positive sample and its corresponding. Okay, I hope this is clear. Can I move on to RNNs?
Yes.
Sir, one very basic question. If I make a WT and see dot product and then do the minus, it will give the same effect, no? Or I need to do the above formula?
No, you have to. That won't be the same, right? You have to see if you do. You are saying, can the minus be moved outside?
No, I am saying that I am multiplying WT and CI, then I put the minus sign, and then I
That's what you have to do, right? So you have to do W transpose C and then multiply it by -1. Yeah. And then
I can do the below formula.
That is also fine. Yeah, both are the same. Okay, both are the same, right? So you could do W transpose C sigma of that minus 1 minus that, or you could do both are same. Yeah, whichever is convenient.
Okay.
Okay, so now we move to, so once you have learned word embeddings, what you can do is you can start solving sequence learning problems. So where the information is given to you in the form of a sequence, we'll first look at, I'll directly go to the architecture. So you are,
So that can you explain the number of parameters in CBOW and Skip-gram?
There is nothing much, right? So in CBOW you have 2 matrices. You have 2 times the vocabulary into the size of one word embedding. 2 times vocabulary size into D, right? That's all in CBOW. And in Skip-gram also it's the same, right? Isn't it the same? No, in Skip-gram it's not the same. In Skip-gram it is just vocabulary into D. Is that correct?
Sir, should not be like calculate for the entire context, entire vocabulary words also we have to multiply, right? Because each and every word has an.
Sorry. So here also it's the same. So here also the W will come from the matrix for word embeddings, and the context C will come from the matrix for context embeddings.
So total number of parameters equals to D into V
D
plus
into V into
plus
2, right?
into 2, or we have to consider the n also. That's what confusion.
N, what is N?
N is the number of words in the context, words in that vocabulary.
No. So see, there are the this is the setup for both CBOW and Skip-gram, right? You have two matrices, and each matrix, one is the target word matrix or word matrix, another one is the context matrix. So there are 2 times the vocabulary size into the dimension of each vector. So if there are if the vectors are 200 and if the vocabulary size is 10,000, then these many parameters you will have.
Okay, for both the cases.
For both the cases, yeah.
Okay, so we should not calculate each and every word because we are predicting the context. I thought we have to calculate n times, like v times. We have to multiply this one instead of 2.
Instead of
instead of 2, it should be d into v square. That's what I thought.
v square. No, right? You have only 2 matrices: word matrix, context matrix.
Okay, we have to add it out.
Yeah. So see, here it's more of the parameters type questions here don't make that much sense because you only have word vectors, right? You kind of don't treat. See, you don't treat every element in this vector, every component of this vector as some independent parameter, right? You are more interested in columns as a whole. So I am not interested in what is the third component of W1. Maybe in a neural network I am interested, right? But here I am more interested in the word vector itself as a whole. So W1 entirety is what I am interested in, not the fifth component of W1 or so. Therefore, I don't treat them so much. You can call them parameters. They are not. It's not wrong, but I wouldn't look at them so much as parameters, but say just embeddings that I'm learning. Okay. So yeah, if you now go to RNN, right? So RNN, we'll first look at a single label. So a common task is document classification or sentiment analysis, where you take a sequence and you associate one label with that sequence. Okay. So how does this work? Now I have an RNN enrolled in time. So okay, there is also, you can also present this using the recurrent connections, but it's easier to look at it when you unroll an RNN in time. So this is, you start with typically a vector of zeros, which is the state vector at time step 0, and then you pass it on. So this matrix U governs the transition from input to hidden state. Okay, W governs the transition from one hidden state to the other, and finally, when you reach the last token, the last point in your sequence, there is a matrix V that governs transition from hidden state to the output. So if some of you had attended my earlier session, I had missed out on this neuron. Okay, please make a note. So this neuron was missing, so I have added it. So this is, each of them can be viewed as in a particular light, right? So W matrix, what will it learn? It will learn how to preserve or carry forward information from the previous state to the next state. So therefore, W deals with the past. So it is a connection from the past to the present. U, what does it do? It tells you what information to take from the present. So it deals only with the present. Okay. And V is, you can think of V as a decision matrix. Okay. So once you have the final state, V will help you decide what to output. Okay. So that is what you have to keep in mind. Intuitively, that's what these matrices represent. Now you have the equations, right? So if assume it's a classification task, so your state will be like this, right? So you take W and multiply it with the previous state vector, and then current state vector, current time step input, you multiply that with U. Okay, that is your, and then you take a nonlinearity. So this is just a linear combination of the previous state and the current input, and then there's a sigmoid nonlinearity on top of it. So that will give you the current state, and you keep passing the state information until at the final step you want to take a decision. So maybe sentiment is positive, negative, neutral. You want to take such a decision. So what do you do? So this state may be, say, some 100-dimensional vector, whereas your vocabulary is like 10,000, right? So you need to convert from your state to your vocabulary, right? So you have to multiply that by a matrix of size 10,000 cross 200, right? So that you do, and then these will all be this is called logits. So without the softmax, this is usually called logits, right? You have to convert the logits into probability. You do softmax. That's the final y hat, okay? And log is the loss, you already know, it's cross entropy. If it's a regression, it will be squared error. So that is known. So what are the shapes? So typically the shapes are Rn. So it could be like R200 here, and D could be R100. Your W is always square matrix. Okay. So the state, remember, is always going to be of the same size. So it's the W is connecting previous state to current state. So it's going to be square. U is input to hidden state. Therefore, it is D cross N. And V is hidden state to vocabulary, right? So therefore, it's V cross D. It's very simple to remember this once you memorize this particular picture. Okay, so what else do we have? We have
XT should be D, RD, no?
which one?
XT.
XT is Rn, right? N need not be the same as D. So N is the input that you pass to your XT is the input that you pass to your Rn, right? It could be different from your model hidden state vector. State vector could be having a different dimension.
Okay.
Right? So
embedding is happening on the ST, not in XT, correct?
see here, so XT is kind of you already have pre-trained embeddings. That's the way we actually present this. So you assume that XT are some pre-trained embeddings, maybe from word2vec or CBOW. You have obtained the embeddings. The embeddings are XT. And you start with that. So if you want to learn the embeddings in the first place, then you should have an embedding matrix that takes one-hot vectors as input, converts them to embedding, and then pushes them. So point that you are referring to probably is if xt is a one-hot vector, then I have to extract some embedding corresponding to that, right? So I usually call it ET. So there should be some embedding matrix that multiplies the one-hot vector to get ET. And then this whole equation will become UET WST minus 1. There, typically ET and ST have the same shape. Okay, but let's not go there. So let's only stick to this for exam point. From the exam point of view, you assume that XT is some embedding vector that has already been given to you.
Okay.
Okay, so and it is okay. So N can be equal to D. It's not, but it could be different also.
Sir, time steps don't play any role here, right? While we are calculating the parameters.
Yeah, so the parameters are shared across time steps. W, U, V. In this case, V is not relevant until the last time step, but W and U are shared across time steps.
Okay, and we can have intermediate outputs also, right? I mean, for X1 also we can have V1 and X2. Like
yeah.
that.
So here in this, so this problem, right? This class of problems where you have, this is like a sequence classification problem, right? So meaning output a single label for an entire sequence, right? So for example, sentiment analysis or document classification, or if you're given a video, for example, you want to recognize what activity is happening in that video. These are all examples of outputting a single label. Therefore, my intermediate outputs are not meaningful. So, but we look at the case where they are meaningful. Okay, so this is a sequence of labels where you are using an RNN to predict a label for every time step. Okay, this is more of a sequence labeling problem. So where every term in that sequence has exactly one label. Okay, this is also one class of problems. So what will change here? The loss function is the only change. So notice that your V becomes active in every time step, and you have the sum of the cross entropy losses at each time step. So that's the only change here. Okay. So is this fine with everyone? Whatever we have done so far. Okay. So the last thing is LSTM. So before that, I just want to explain one thing, right? Why the LSTM is probably needed. So if you go back to an RNN, typical RNN, maybe I'll just take this RNN, right? So if you look at this state, ST, so ST is doing two things. So ST is doing two things at the same time. One is it is maintaining or it tracks, or what, how do I put it? It stores the information in the first t time steps, right? So it's like history. You can also view the state as a history vector, right? It has the history of whatever has happened in the first t time steps, so that I can pass on this information. In fact, first I would, maybe I can use t-1, right? Yeah, so st-1 holds the information in the first t-1 time steps. And then with information from the current time step, it updates itself to st and it keeps on passing this information, right? So one thing it does is it acts as a context vector. So it acts as by storing information in the first t time steps, right? That is one job that it does. Now, if you look at this image, right, it does another job also. The same ST is only passed through this output neuron to arrive at a decision. So it's also doubling up as a decision. It also helps in making a decision. So it's like also a decision vector. Helps in making a decision at time step t. Okay, this is like kind of overloading the state. So it will be good if you can separate these two responsibilities, right? So it would be nice to have one vector that just acts as the context, which passes on information one time step at a time. And there is some other vector which takes care of taking decisions at each time step. Okay. So the LSTM kind of solves this problem to some extent by splitting the context and decision into two vectors, ST and HT. Okay, so the ST, what it will do is it will keep propagating this state information from time step to time step. And then finally, the decision making will be given to some vector called HT. Okay, so that's what happens. Now, if you directly go to the states, there are like too many variables here, so it might be confusing. So what you're doing is there is some previous state, okay, context, and then you are generating a new context vector. Okay, so this ST tilde is the temporary context that you are generating based on the previous output and current input. Okay, so you don't just combine it with, what would you like to do? You would like to combine it with the old context vector and create the new context vector. Okay, but then you don't want to just combine them blindly. Instead, what you do is you introduce this gating mechanism. So I want to forget some parts of my context. So I do that using a forget gate. I want to select some parts of my new potential context, right? Therefore, I use an input gate. Okay, so these gates, what are they? These gates are, again, functions of the previous time steps output and current time steps input. Okay, all gates are configured that way. Now, once you have your gates, you can create your new context vector ST, right? So this is the whole gating process. And once you have the context vector, right, ST, that is going to go to the next time step. No changes there. But then at the output, you have to decide what part of your context is necessary for decision making, right? So remember, this decision making is with HT, and the context is, or the history is with ST, right? So therefore, you need something called the output gate to decide what to output at the current time step. Okay, so you have all these gates are not static entities, so they are determined, or they are kind of controlled by learnable weights. So they are,
It's 8 o'clock.
WI, WF, WO, and UI, UF, UO. So these are all going to, once you finish the learning, these will kind of contain the information of what to select. So WI, for example, will have the information of what to select from the previous output. UI will have information about what to select from the current time step when it comes to the input gate. Likewise, FT, right? So WF will know what to forget from my previous output, or and UF will kind of remember or know what to forget from my current time step. Okay, so I'm just very crudely representing these things. But yeah, so that is with respect to the gates, states, and the output in LSTM. So any questions here?
So every gate will have the same dimension as ST and HT, right?
Every gate will have every matrix in the gate, you're asking?
No, gate, IT, FT, OT. Because we are using the dot product to
Yeah,
find
you
out
are.
ST,
Yeah,
right?
they have to. So this is this is like a element-wise dot product. So the state, the candidate state, gates, they should all have the same dimension.
Yeah, even HT also same dimension, right? Because end we are calculating using ST.
HT, correct. Yeah. Yeah. So HT, ST, IT, FT, OT, all of them have to have the same dimension. Only then can you perform the respective operations.
Yeah, and parameters will be shared, right? In
Yeah,
every.
WI, WF, WO, all these Ws are shared across time steps.
Okay, so while calculating, we have to calculate one
For
time
only
or
one time step as so to speak, right? You should not. So if there are 10 time steps, you don't have 10 different WIs. You only have one WI which is reused in all 10 time steps.
okay, so we have to multiply W and U dimension into 4 times because we have 4 bits, right?
Yeah. So yeah, see, for RNN, right? I'm not talking about transformers at this stage. For RNNs, if you are asked to calculate parameters, forget about the time steps, right? So time step is going to play no role in the parameter computation, right? So you are only interested in, so even in, yeah, so yeah, for RNNs, please don't worry about the time step for parameter values.
Okay, we are not sharing this one.
Yeah, they are shared across time steps. Okay, so that is 1 hour. So I am kind of done. Okay, no other questions, right? From weeks 9
Sir,
and
sir, what is S tilde T?
so S tilde T is your candidate new state, right? See, you need a, so you know what to you have your previous context. Okay. So with your previous context, what you can do is you can modify it by using the forget gate, and you can kind of tell what to forget, okay, or what to remember. So what to remember. So forget gate, when it is, if there are zeros somewhere in the forget gate's value, in the forget gate vector, those things will be forgotten. Wherever it is close to 1, those things will be passed on. Okay, so you kind of decide what to pass on to the next time step. The input gate is telling you, you also need to know what to select, right, from the current time step. So that is what S tilde is, ST tilde is,
Got it, sir.
right? So this is your usual RNN state in some sense. That's why there is no subscript here, right? So this is how your RNN state is. Okay, if everything goes to 0, or rather, can kind of reduce LSTMs to RNNs by getting rid of the forget gate, turning the input gate to all ones, right? So that will that recover RNN? I don't know. Yeah, so that's a separate discussion. Let's not go there. But ST tilde is giving you a candidate current state, and then you select what you want with the help of the input gate. Okay, so
So, sir, any possibility to get a question on back propagation of the RNN?
that is there, right, in the this thing I had shared, one example question.
Back propagation of the RNN? No, I believe.
Oh, you want so full blown back propagation using big W matrices, the ones like the ones that you see in graded assignment, right? You're asking about them.
Yeah.
Uh so we won't have time to do that now, but see, as long as you understand the basic ideas, it's enough,
Okay.
right? How do you basic back propagation? If you know how to use the chain rule, you should be in good shape.
Okay.
Okay, I think
I have one thing. So can ST's function be changed to tan H instead of sigma? ST
yeah,
readers.
it's a good point. Yeah, actually, in the original LSTM paper, they used TANH in some places. I
Yeah,
don't
I
know.
got confused with that only.
Correct. Yeah, you are right. So I don't know why we are using sigmoid though everywhere. Maybe for convenience, we are using sigmoid everywhere. But yeah,
Yeah,
you're
in
right. So there
papers
are
also I got tan H only in
yeah,
previous
yeah. You
papers.
can. So see, the gates have to be in 0 to 1 so that you kind of they are soft probabilities, right? So in some sense, so they are. I think these are all sigmoid, right? You are talking about TANH.
Yeah, only ST did only.
Ah, okay. This is TANH, and I think some other. This also was TANH in the papers.
That one was sigmoid, I guess, because that should be a probability, right?
Ah, okay. This also is probability, correct? So not okay. I should not probably be calling them probability, more of
Yeah,
something between 0 and 1.
yeah, 0 1.
Yeah. But you're right. So there is TANH used in some places, especially in the original work. In the blog that I had shared, also they use TANH. But for the exam point of view, assume that everything is sigmoid.
And one more thing I want to ask, like, if sigmoid is there, then there is a chance of vanishing also, right?
That is right. But then the whole idea of LSTM is to kind of tackle that problem, right? So they, by knowing what to, by introducing these gating mechanisms, yeah, you're right. I don't,
Even I was confused, like, only we know that it can be, like, ranges is there, but 0 also is included, right? 0 to 0.5 or 0 to.
yeah,
That's what
I
I
don't know
want.
most. I am like not very sure about that. I might have to dig up. Yeah. Anyway, so I think Manoj is. Let's do 11 and 12, and at the end we'll come back. Okay.
So I think
Manoj,
the vanishing gradient problem is with the RNNs. Hello. Uh, okay, so we'll start with week 11 and week 12. Let me share my screen.
okay, sir.
So, okay. So in week 11, we have two things. One is what is encoder-decoder model, and then what is attention mechanism. And in week 12, we'll see how on top of attention, like what improvements we can make and make it a self-attention mechanism out of that. And then using self-attention, what is multi-head attention, right? So there are a few topics in week 11 and week 12. So uh, okay, so if you have, let's say, a problem of textual entailment where there is some premise, right? So premise and some hypothesis is there that if it is raining outside, you want to predict hypothesis is the ground is wet, is it going to be there true or not, something like that, right? So like many other problems, for example, machine translation, where I'm going home and the translation of that is in Hindi or something, right? So uh, how how can you do it with encoder decoder model? So in both the cases, you can see we have used RNN architecture. So this is RNN architecture where we are passing each token at a time, and we are creating a, a final representation embedding, right? So this embedding we can send it to the decoder, and there also again same RNN kind of architecture will be there, and it will do the prediction, right? So something like that. Now what changes is, or what sometimes changes is, so here both of them have similar kind of loss function, but sometimes you'll see different kind of loss function. Let's say if it is used a true false is what you wanted to predict, then of course you'll not use softmax in the final layer, and most likely you might use uh, a sigmoid level, or something like that,
So,
right? So
so,
yes.
so I have a doubt here, very silly question. So, how to differentiate the this what we call it submission function, like when there are a lot of submissions, and this operator like from 1 to I, it goes like this. In question paper, if such a loss function comes, then and we have to back propagate it, then how to first differentiate it?
um okay, so for this loss function differentiation, um you need to understand how you can do RNN backpropagation, because it is same as that. So you can see this is just log p and something, right? So how do you do softmax backpropagation, right? So when we had final layer as softmax in ANN, and then out of that we used to say some y prediction, right? So now how am I using y prediction here? um I'm taking um so this log p of this, right? So whatever this part is, it's the same as the softmax, right? So uh, uh, yes, so this is softmax, but here you don't know what is the true thing, but if you know, then how will you do the back propagation of this? uh, so from softmax you directly have to do this, right? So that then, I mean, it's very difficult. So good part is this, at least this much difficult question won't be the quiz, because it will take, I don't think so you can do it in 1 hour. So at least this much level of differentiation is not going to be there. So it is just for understanding purpose that you can do it. So softmax, how do you do that? Softmax you have to understand
So
first.
we can use the formula of softmax, and then it's e raised to power
Yes,
e differentiation is same, and whatever with the bst plus b, if it is also a parameter, then it will also be differentiated again,
yes. So
like this.
so then that is the thing. So if you know how to differentiate RNN, then that is the same thing, right? So here we are sending the final output of RNN, or it was RNN only, right? So BST plus B of software, something like that. So it is almost same as the RNN differentiation,
Okay,
uh,
so
right? So uh, okay. Now, so what we are doing in encoder-decoder model is we are encoding first the information using a RNN model. Then we are passing that as a S0. So here we are passing it as S0. So till now we in RNN we used to maybe randomly initialize S0, or sometimes train it in some way, or you can just initialize it with zeros. Anything is okay. Right. So but better way to do the initialization, or better way to give S0 is this way, right? So they realize that if we train a RNN model, and it will learn all the um, embeddings of this, and then if we send it, then that will give a better result than randomly initializing it, something like that, right? So that's why we are here in encoder decoder model. So and when we reach to the decoder, we have S0 as HT, which we have learned from here. And then again, like we'll start the same RNN process, and finally we'll do the softmax computation, where we'll take whatever is predicted here. So the is there, but what could be the correct in this case, right? So we have to add all of them, right? So you can see from T1 to T. So at each point you'll take the softmax calculation, and you will add right. So as many t is going to be there, that many this softmax going to be that, right? And you are taking log of that. So this p, whatever you are getting p here, you are taking log of that and you are adding that, right? So that is the loss function in this case. Now same thing we are doing machine translation. Nothing much changing here. Uh, yes, right. So in training, just remember that in training we do something called teacher forcing, where whatever we have predicted, in reality we know what we should have predicted, right? So we have the x and y pair, both of them. So from y we take the word which should go here. So for example, we are sending this, and this is the correct one. If it would have predicted something different, let's say ja in the first place, I wouldn't have sent it here. I would have sent me only, because that's what is the best way to train the model, and that's called teacher forcing. Right. So this only we do in while training the model, but while testing we just let it be, like whatever output comes here, we send it back to this, right? So just remember that. Now there is some issue with it, that we are not able to learn the embeddings much better, and we are relying too much on this one S0 or one embedding, uh, right, to understand the whole sentence here. So this is very difficult task for S0, that I have to remember all of this, and only once we are giving it to the encoder in the starting, in the beginning, and then we are losing. It might the information is losing or something like that, right? So another option could be that maybe we can send S0 at each timestamp. This could be one option. So something like that they tried, and they've come up with one better solution of that, which is attention model. So in that, what we do is we let's say I want to compute attention here. So all the embeddings of this, and whatever st-1 I got, I take some form of mathematical calculation between and find the score of that, right? So what that mathematical calculation is, something like that, right? So each hj, so whatever is coming from the encoder, I'm calling that hj, and whatever is coming from the here, like it should be st-1. Okay, just small mistake. It should be st-1 here. Okay, now st-1 is whatever it has predicted here. That is st-1, so which should have gone to this this timestamp, right? So we'll use that st-1 and all the hj's to compute attention score between each of them, right? So between h1 and st-1, we have to compute a score. h2 and st-1, we have to compute the attention score, and similarly till all of them, right? So here you can see it is h5, but whatever could be, right? ht finally in this case also, right? So t here. So this t and this the encoder t and decoder t are different. Okay, just remember that they are both different things, and that many attention score I need to compute, right? So how I'll compute is, I'll for each, like so one for h1, if I want to compute, I have to use this, right? So some I'll introduce some form of parameter in terms of metrics and all, right? So I'll give this u attention parameters to hj, w attention to st-1, and then I'll take 10h of that, right? So what I'll get, I'll get some kind of a singular vector, and that I'll multiply with v transpose of attention, right? So v transpose is again another form of just a row. So v attention will become row. That's a row of parameters, right? So again, this could be a matrix. This is going to be a matrix, but this v attention is going to be just a column, or you can say one dimension or form of our parameters, right? So that many parameters will be there, and this all are parameters. So v, u, and w are the parameter in this case, and using that I can compute e, j, t, right? So this is for one only, like for example h1 or H2 or anyone, right? So I have to do for all of them. So I have to repeat this process 5 or 6 times to get all the attention scores. So once I
Sir,
yes,
sir, tan h of W is t minus 1 is there, right? That whole
NH
function, yeah, tan h and whole function inside that bracket. That is the actual state of the function, right? Actual state, right? It's the state
H
itself.
is a state, yes, for encoder.
Encoders, like encoder state, right? It's ST,
Yes,
right?
yes. So whatever we are getting here, right? So this H J is the one which I got here. So this H1 here, what I'll get is H2, something like that, right? So from RNN we have produced this. See, you can see this. This is HJ, right? So I use as
Yeah, that is the input, right? Input to that softmax function, right? Tan h function, right?
yes, correct.
Yeah.
Okay. Now okay. So now
So where these alphas are used, the weighted sum, so the
yeah,
plus
I'm
sign
going
is
there. So as I'm going there, that what are you going to do with it? So let's say you have computed, so here also ST minus 1, right? So you computed this EJT. Now, now what will happen is you might get them in some numbers, right? So let's say some numbers are there, but how will you know what is the proportion of HJ I should uh, consider in my decision that this one should contribute this much. So for that contribution part, we are making or we are normalizing using softmax, right? So softmax will normalize it. So finally, we'll have all this alpha JT. If you add them, it will become like it will be in 0 to 1, but the summation of that will become 1, right? So now you can so whatever the number is, you can take that much value that the sentence will give while predicting the home. Like for example, I want to predict the next sentence stop here. For example, stop I wanted to predict. Now this how much this one will contribute and how much H2 will contribute, H3 and so on, right? So this contribution will be using softmax of EJT. So all of them I'll take softmax and I'll call that alpha JT. Now so that's what, how will I say that what contribution? I'll multiply all the uh, all the embeddings or all the HJ with that number, right? So let's say H1 I'll multiply with alpha 1t, right? So I'll multiply with alpha 1t. Then similarly I'll multiply alpha 2t with H2 and so on, right? And if I sum all of this, alpha 1t, 2t, something like that, then the final uh, embedding I'll get, which I'll call as CT. So this is called context vector, right? So this context vector has information about which word has what importance and uh, yeah. So that would be right. So which word has what importance in predicting the next word of my decoder. So that's what this CT will have. Now again, like so we
Sir, where are the context vectors present here? Which channel represent the context vectors?
which all
Represent the context vectors you are talking about.
this CT, right? So this CT is context vector.
Okay, sir.
I got it from multiplying alpha JT, which I got in from all of them, and then each individual vector H1, H2, and so on, and I'm multiplying them with respective alphas, and I'm summing them, right? So I'm summing all of this individual vectors so that I'll get CT. CT is the final vector. Okay. Now the final vector of
So,
CT.
so
Yes.
one more doubt, sir. Why we are passing this all vector at the last point, the stop word? If we pass it at the starting of the sequence, then it could have predicted much better sequence because it is the weighted of context. So why
Yes.
we are
So
doing
no,
it
no, we
last?
we don't pass it at the last only. We pass at every step. So we pass it here also, there also, here also, there also, everywhere. We do the same process. So you can see in RNN what I'm doing ST minus 1. So EYT minus 1 and CT, right? So at each timestamp, I'm going to compute this CT. C0, C1, sorry, it starts from C1, C1, C2, C3, and so on. Okay. So at every timestamp, I have to do it. This process is repetitive. Okay. And the rest of the things is same, like you have RNN, you pass ST minus 1. So this is the prediction from the previous one. For example, home we are sending here, right? So this home and context vector, I'll concatenate them, something like that, and I'll pass through the RNN, right? This is this blue RNN, and it will give me the final ST. Now, what will I do with ST? I can so I have to multiply with V parameter plus B. So this is same as RNN function which we have. So the only thing changes is how ST is computed in this last part, right? So that will the loss and algorithm remain same. So whatever we saw here, this loss function and all remains same. Nothing changes here. Just one intermediate step was introduced, which is this attention mechanism. Okay. Now, what you can do is you can put all of this attention or whatever alpha score you get into a matrix form. So this is another different example, but what we are doing, I enjoyed the film Transformer, and this is a Tamil translation of that. So in this case, if you want to, let's say alpha 4 to, right? So this guy, what does it tell you? That this Racinten here and the Android, right? So this Android, how they are related to each other. How much attention should I give to Android while I'm predicting this Racinten, right? So that's what this will. And similarly, alpha 3-4 will tell you a different example. So it starts from alpha 1, right? So when I will be I want to compute the similarity between nan and I, how will I do? So this H1 is I, right? And nan is this one, right? So that is alpha 1. So of course I would have computed at that point when I was there. So now I'm in this image, I'm at the 4th point, but I could have been in that point also, right? Yes. Now same thing. What I just explained there. Now we are taking exponential. So this is same as the softmax function of EJT, right? So that is the same thing I've written here. Alpha TI to get alpha TI. Now okay, so this will help you in getting the attention score, and same thing you did, right? Now we wanted to the issue was that each timestamp I have to compute this attention score, right? Alpha 1. So alpha, let's say some j and 1, right? So all the alpha j's, for example, H1 to H5. Similarly, alpha j 2, again some different thing, right? So then I have to compute this at each timestamp of the decoder, right? Now, how can I make this process parallelize? Like I want to do parallel. I want to compute this parallelly, right? Now I don't want to compute it individually, but parallelly I want to compute so that I can increase my computation speed. So to increase the computation speed, what they have done is they said that whatever your Hj is, right? So Hj is like here this one, right? I or anything you can take. Now you multiply it with Wq. So this will be a learning metrics you will introduce. So of course you will randomly initialize it, and then later on you will do the back propagation and update the weight. Similarly, you will have another learning metrics, which is WB. Third one is WK. So this 3 we are calling as query vector. Or whatever it will produce is called query vector. This is called value vector, and this is called key vector. Right now, so WK QKV are called respective linear transformation of parameter. Right? So what does it help you? So initially, so first, like in attention only, what we did is we were used to compute score between ST minus 1 and HJ, right? So same procedure. Now we'll do it with Q1 and KJ. Right? So KJ is some K j. You can take any one, and Q1 is the one, right? So not. So this example is for 1, but of course you have to do it for same thing for Q score of Q2 and then all the KJ, right? So this process will be.
calculation?
Sorry,
What is the score calculation?
score is the one we did earlier, right? So this is score.
It's
Softmax.
dot product basically. It's written.
Yes. So this now we'll see. So what we have do is, so using score Q1 Kj, we are computing this thing. First, we'll do Q1 with respect to K1, K2, K1 to K5, all of them, right? So and that I'm calling as E. So earlier we used to call Eij, right? Same thing here, E1. Uh, E1 I'm calling because I'm using Q1. If I would have used Q2, then I would have called E2. So this is same as E1 E1J or something only, but E1J could represent this only one element of this, right? But we have the whole vector. That's why I'm representing as E1. Now I have to take softmax over that, which I did in that attention also, right? So here we are doing this first, and then I'm taking softmax over it, right? So EJT and then taking softmax over that. Same thing I'm doing here, nothing different. And then whatever the alpha values I got, I'll call that as attention score. That I have to multiply with VJ. So what I used to do here is I used to multiply with HJ, which I was getting from this only, right? So HJ was produced at the each timestamp here, but now I'm not going to do that. I'll get HJ from multiplying this value, and Q value I'll get from this, and K value I get from this, right? So something like that. That is the only difference thing I'm doing. That Q and K I'm getting using learning parameters, and not directly I'm keeping whatever ST minus 1 and HJ were, right? So I'm introducing some form of learning to um, to reduce my computation or to increase my computation so that I can parallelly do it, right? So to parallelly compute all of this, I have to introduce this parameters, right? So they have done it, and this is the result of that. Okay. So this is Z1, and similarly you will do again with some Z2, some Z3, and all, right? So the process is same as that. Now, how will you do that thing? The whole thing parallelly, right? So this thing we are doing for one only, right? So let's say I wanted to do for like let's say sorry, not I, but I enjoyed the film Transformer, but I want to do for NAND, right? So this one thing or one time I want to compute this attention score, I will do it this way. Okay, but how will I do it for the whole thing, right? Now I want to compute for the all of them, right? NAND, transformer, whatever this rest of the words are, I want to do that, right? So for that, I'll introduce this metrics now. So we had Q QI and KJ, right? So the same thing we have to do, but what we'll do, we will take the whole thing, which has all the you can say all the so Q, all the columns of that are Q1, Q2, Q3, Q4, right? So if you transpose them, it will become rows in this case.
Sir,
Yes.
it is Q transpose K or Q K transpose?
So both are the same thing, but we are using this notation.
But in slides in shared in G space, it is Q K transpose, right?
No, it is this only, right? Q transpose K.
Okay, sir.
Okay. Okay, so we have this. Okay, now yeah, so Q is like this, and K is also like this. This some K1, K2, K3, and so on, right? And similarly, V will also be like this, right? So now this is something like you can consider it like a matrix of all of them. Now, if you multiply Q transpose K, so you have to do some form of scaling down so that the softmax is very um, like it get affected by the values, right? So if it has some higher values, like larger values, then that will get more softmax values, which we don't want. We want them in some moderation, right? So this moderation, to bring this moderation, we did divided by under root dk. And another reason is like I don't want to go into that, but something like we wanted to reduce the variance of this multiplication, right? So this, if you compute the variance of each matrix, how we can reduce the variance, you can do it using under root decay, right? So that is another reason. You don't need to know the reason, but we are doing this under root decay so that the softmax values will be much better in this case, right? So that's what we'll do. Now we are computing all of them parallel, right? So this will multiply with all of them because it's a matrix multiplication. Similarly, all of them will multiply with all of them, right? Q transpose K. So you will take softmax of that. Just remember that you have to take the row-wise softmax. So somewhere you will, whatever value you get, this matrix will look like matrix. But now you have the option to take column-wise softmax and row-wise softmax, right? But you have to take row-wise. So this you can see here, Q1 K1 will be there. Similarly, Q1 K2 will be there, and in this case it will be Q2 K1, Q2 K2, and so on, right? So you have to take row-wise softmax of each of them, and whatever values you get, you will get a matrix only. Now that matrix should be multiplied with V transpose, right? So V transpose will also be in column form, so you have to make it as a row-wise, okay, and then you have to do this multiplication. So this final whatever you get, that is the Z, the final Z output. Okay, the Z out. So in this, the attention is this much. The softmax part is called attention, but the whole output is the final output. Okay.
So DK's value would be T, or what is the value of DK?
So dk is the value of what is the dimension of the K matrix, right? So WK matrix or sorry, not WK, but whatever this KJ you will get, right? So this finally you'll multiply with all of the HJ, then you'll get some form of K matrix, right? So it is going to be square matrix only. This K matrix, not this one, but the final K matrix you get, right? So whatever the dimension of K is, so of that square matrix, you take that as a DK.
But DK is a singular value, right?
It is a single value, yes.
Yeah. So K's value will be also singular.
No. See, you are taking, let's say this is a K matrix. Okay, it is of size 54 cross 54.
Yeah.
So
So
DK
here
will be
this
54.
example, in this example, 64 cross T is there. So DK would be 64. I'm asking.
Will DK will be 64? That is correct. Yes. DK will be 64 in this case. Yes.
DK would be 64. Okay.
Yeah, that is correct. Okay, so here the some dimension computation is there. Now, of course, if you multiply, let's say, T cross 64 with 64 cross T, right? So this is Q transpose and this is K. You will get T cross T matrix. Right? So here you will get T cross T. Now, if you divide it by a scalar value, so this is just a scalar value, right? Under root 1 by 64, which is 1 by 8. Now you can do that. So it will not change the dimension of this matrix. Again, we'll have T cross T. You take softmax, that will also not change the dimension of this. Again, T cross T. Now the T cross T you have to multiply with the V transpose, which is of again, maybe you can take any different dimension also. Some V dimension you can take, and that is also going to your T size. Like the number of columns will be in T in that. So if you take it should be V transpose here. That will go there. Matrix multiplication you have to do here. So now T cross T you are multiplying with T cross V. So V is I have taken some number. So finally you will get some T cross V in this case, right? The dimension of that. Now you can take 64. So that's what they have done. That's why it is T cross 64. Okay. If you take T, but you have the choice. I'm just saying that you have the choice to have any other V in this case other than 64, and you will get a different value. But they have taken 64. That's why the value is T cross 64. Now, what are the parameters in this, right? So if we see the parameter calculation in this, the parameters are this WQ, WV, WK. So these three form of parameters are there in self-attention. When we'll go to multi-head attention, then there will be one more WO will be introduced, and then that is also parameter. Right? So whatever this metrics are, just remember this: all these metrics are always square metrics. W, Q, K, V are always going to be square metrics, most likely. Give me a minute. Just I'll, sorry, it's not needed that it's not necessary that they are square metrics. The Q and K are going to be the square metrics, not WQ and WK. Okay. Now what other thing we can do is we can have why should we have only one attention? We can have multiple attentions, right? So same thing if you repeat again and again, same thing like here I'm doing it, here again same thing I'm doing, and same thing I'm doing multiple times. I can do that, and if I do that, then I need to do something called concatenation, right? So I have to add them somehow. Now I can concatenate them, and then I'll pass through a linear layer. So just remember that linear layer is linear layer without activation, without any activation. So some form of weights are there, some weights are there. You just pass through that. Right? So that's what is a multi-head attention. Now, what kind of issues could be there is, let's say one issue could be that you might concatenate and you get a value which is not a size of embedding, right? So let's say you started your embedding with 512 here, HJ was size 512, okay, and you didn't end up having 512 here, right? So here we got 512. That's what they are saying, but let's say we didn't get it, then what options you have? Now you'll sorry, after linear layer you didn't get it, then what options you can have? So you can actually introduce a WO matrix which will help you in changing the dimension of, and another form of learning parameter was required, so they introduced WO in this also. So this concatenation of each of them and passing through linear layer, then you are passing through another form of this linear layer, sorry, this linear layer itself is WO, right? So this linear layer itself is WO. Okay. So concatenate all of them, then pass through another WO here, and then you'll get the multi-head attention. Okay. Any confusion here?
So then the dimension of each matrix in WQ, WK together we are getting on attention matrix, right?
Yes.
That would be 5 and 2 by n, right? Number of hits.
5 and 2
by n.
Yeah, you are talking here scale dot product.
Yeah, scale dot product matrix, because we need to concatenate it, right?
Yes. Now, no. You might get it. So let's say you might get here of size. Let's say one is T cross something. Let's say 64. So another output was here T cross 64. Similarly, here finally T cross 64. Sorry, T cross 64. Right now you have to concatenate them. So as many heads could be, but finally. Now they mentioned 5 and 2, so this is coming from somewhere. Like I have taken this image from the slides, but you can have
So
whatever you concatenate and get.
64 across 8 only will come 5 and 2. So that only will concatenation work, right?
Yeah. So if let's say n is head, n means number of heads are 8. So in this case it is 8. Then you'll get 5 and 2.
Yeah. Then we have to divide by 5 and 2 by 8. We have to divide. That would be the attention mechanism matrices.
Yes.
Okay.
Yes.
And this 5 and 2 will be the last matrix size also, right?
Yes. Yes, correct. So finally, whatever input we gave, input embedding size, that should also come out from the final output of this multi-head attention. Okay. So we gave 5 and 2, then I should get 5 and 2. If I send, let's say 16, then I should get out at 16. Like whatever I do internally, that is my computation, but output should be of size 16 because that's that was the size I gave as input. Okay. Okay. Now we have computed the multi-head attention. So now let's see what is decoder layer and how does it look like. So if you see encoder layer, then in that there are two things only. One is this FFN layer, right, and below that will be a MHA or multi-head attention layer, right. So there's two things only there. The third component of cross attention won't be there, and mask attention won't be there, but just multi-head attention. So the one which we saw here, this multi-head attention will be there. That is encoder stake, right? So this encoder layer. So this is called layer, and this layer will, if it was encoder, then it would have looked like this. But this is a decoder, right? So if it is decoder, then it will look like this. So it will have three components. So I'll explain what is individual of this. Let's see what is there. So let's see what is masked multi-head attention. So where it will be useful when so what is happening is, let's say if I send all of the inputs and then I'm asking to predict it, and I'm giving all the outputs also, then why it should learn, right? So the learning might not happen. That is the issue. And what they've come up with, they've come up with solution that, let's say first timestamp here, I'll say that I only have one word only, this and nothing else I have. So that's what I wanted to do, right? So how will I do? I'll give one input, but I'll just mask it, right? So I'll not show it to the encoder, decoder.
Encoder
Yes.
always have two layers only.
No. It could have any layers. You can choose any layers. So here if it is no layer, see, layer is this is the layer. This
Yes.
are the maybe components of a layer.
Okay.
Yes, encoder have these two
So,
components only.
Sir, why we are masking the sequence? Because if we are doing so, then we can use RNN itself. What's the need of encoder decoder then?
No. So this computation will happen parallelly, right? You are going to send this whole matrix parallelly, and it will happen in one timestamp only. Like, you'll not do it multiple timestamps, right? So this parallel computation will be very fast. And in RNN, it was slow. We can't do it.
Okay, sir.
So step by step, sir, in RNN.
Yes, in RNN, we would have sent the first element and then maybe predicted second one, right? So something like. But here we are going to send the whole thing.
Okay, sir.
Sir, should we remember all these equations or the short texts?
These equations?
Yeah. Yeah. There are
Yeah.
two
So
things.
you need to remember some of this attention and some of this self-attention also, right? Attention, self-attention, if you know, then the rest of the things is the same thing, right? So you are just concatenating it, adding it. Like, you don't need to remember concatenation or something. That is okay. But the attention, self-attention is yeah, it might be needed. Okay, so now we are we can mask using that. So if I do the masking, then I'm calling it as masked multi-head attention. That's all. Like, I just have to mask it, and rest of the process is same, right? So whatever I was doing here, the computation of QK transpose, sorry, here I was doing this QK transpose computation. But in this case, just remember that earlier my QK transpose has all the values shown to me, but now some values will be masked using minus infinity in that, right? So so that I won't have. Okay, so what you will have is wherever minus infinity is, if you take softmax of minus infinity, so what is e power minus infinity? It is going to be 0. Okay, so rest of them will be zeros only. Okay, now yeah, so that is masked self attention. Now another is multi-head cross attention. So okay, let me go to multi-head cross attention only. So what we do is, from encoder we take so whatever encoder will give you some form of matrix, right? So you will get some form of matrix here from encoder, that you are going to multiply with WK and WV, and whatever you get from that, you're going to call as K2, V2, or any number doesn't matter, but that's what key and value you will take from encoder. Just remember that key and value are coming from encoder, and the query will come from the decoder. So I've done the multi-head attention computation or masked multi-head attention computation here, and that I'm going to send it to this, right? So okay, I haven't maybe explained this part,
Sir,
but
that means K, the matrix K equal to WK into X, right? Coming
yeah,
from encoder, right?
yes, but this time X is coming from encoder. Like for
Encoder.
example, here also it will be WQ1 time X only, but this X is from the decoder.
Mhm.
So you can name it differently, maybe X1, X2, or different whatever
Yes.
thing, but that's what we have to do. Right? So whatever is coming here is going to multiply WQ1, but encoder whatever is coming, we are multiplying with another matrix. So this subscript is there, so that you know that this is different weights, not same weights. And so this weight and this weight are different. Okay. So okay, now you can compute again the cross attention. So whatever you did, right? So you'll get Q from this and K from here, right? So Q transpose K, you'll multiply both of them. You'll take softmax of that, right? So Q transpose K, you'll take softmax of that. Of course, you have to do some form of scaling, and then you're going to multiply VT, right? So which you will get here, right? So V2, you can name two to all of them. That is also okay. So this is called cross attention. Right? So that is cross attention in this. Now finally you will pass through a feed forward network. So feed forward network was what I guess we haven't seen it, but feed forward network is so let's say this multi-head attention, or let's say multi-head cross attention, anything is there. Now you are going to pass this is Z, right? So whatever I'm calling is Z. You'll have some form of weights here, right? So W1 is the weight and some bias here, right? And you are going to pass through max of this. So this kind of, you can say, linear layer, right? Kind of this, which has W1 weights, and this has activation of ReLU, right? So ReLU activation, if you see it like that, that is the same thing, right? What I mean is this layer. Okay. Now, so this weights are with W1, okay, and some form of bias also you can introduce. So another weights also you will require, let's say W2, and that will have B2 parameter in that, and there will be no activation function, just pre-activation, you can think, or linear layer, right? So this is how it is. Now, why we are doing it? So just think that we have 512 size of embedding. Now we are expanding it to 2048 so that you can learn something. So for learning purpose, we have to expand, or we are introducing more weights to it. So more weights will be introduced, and that will help in learning process. And then since I have increased the size of my input, now it is of size 2048, right? So I have to shrink it also, right? So when I said that whatever I send, but I always get back whatever input I gave, right? So input size and output size will always have to be same, right? So for that purpose, I need another layer, and that's what the feed forward layer will do it. And that's what is in the decoder architecture, right? So decoder architecture has three parts: masked, cross, and feed forward network.
Sir,
If it
why
was,
we need cross attention?
so how will you take input of encoder? So you are getting encoder here, right?
Hmm.
So here, let's say you sent this English sentence, right? So give me a minute. So somewhere it should be there. It is for example, this is there, right? Just think that I sent, I enjoyed the film and transform, right? So this is in the encoder. Now I need to send it to the decoder, right?
Yes,
I
sir.
need to send it to the decoder. So how will my decoder will take that information and process it? That encoder information will be taken and processed using cross multi-head attention, a cross attention. Okay.
Okay, sir.
Yeah, here.
Sir,
Uh,
how can we calculate the L value in the FNM?
uh, Sorry, I didn't get the question. Can you repeat?
If you go scroll down
Last.
in feed forward network, we have the L value, right?
L value, right? So what is it?
How will we
Um,
calculate that dimension?
the dimension will be based on whatever W1 is given. Let's say your, for example, let's say a vector of size 512 you are sending, and there is an input of this layer, right? Will be of size let's say 2048, right? So, and how many weights will be there in between 512 and 2048?
Okay,
Wha-
that okay.
So, this
2048 if I
output is of 2048. That many hidden neurons are there. Neurons, right? So, number of neurons. You can say number of neurons in my hidden layer. You can take it as hidden layer.
okay. So will it not be like double?
No, you
That's
don't
what.
have to calculate it. You have to
Okay.
decide it. You have to give that this many neurons I want in my hidden layer.
Okay, so while calculating the parameter on the FNN, we have to just calculate 5 and 2 into the given value.
Yes, so the number of weights will be that many, right? 512 into 2048, that many.
Into 2,
So
right?
yeah, so the idea is they wanted to expand it by, I guess, 4 times of it, right? So 4 times of the input they wanted to expand it. So that's why they chose 2048.
Yeah, that's what. Why did they expand to the 4 times? That's what.
Uh,
Okay,
to increase the learning parameter, right? So you have this input. So what we used to do in ANN, let's say I have this
correct.
input,
We distinct,
then
yeah.
I have some hidden layer, right? Now,
Yeah.
how will I choose number of neurons? If I have more number of neurons, the more better the learning is, right?
Yeah.
That's what the idea is. So they are following same idea here.
Okay, it's not dependent on the number of layers, right?
No, nothing. It is not dependent. So it is just based on pure the whatever ANN, like so more learning they wanted, and that's why they chose this number.
Okay. So this number will be given in the question paper, right? What is that? Like
Yes,
this.
most likely it will be given. Yes.
Okay. And if you go up, I had one more thought. In softmax layer, we are connecting, right?
Softmax layer we
Uh,
are
in encoder to decoder, we have a
okay.
connection,
Encoder to decoder. So cross
right?
attention we
Uh,
are here. Yes.
yeah. So
Okay.
here we are taking the key and v value, right?
Yes.
So the k and v value we are taking. So already we have taken the z value from the self attention, right?
You're saying this key and
No,
already
no, no,
taken, right?
not this one. Encoder we had a self attention, right?
Yes, yes,
From that we are taking the softmax. From there only we are taking the wk and wv.
correct. No. We are not taking from there. These are just different K and P. They are totally different. So this new parameters were introduced, WK and WK K2 V2, which are different parameters. So in
Okay,
encoder
they are not
also,
the encoder parameters.
no, they are not encoder parameters.
Okay, that's what this confusion.
Yeah, no, they will be completely different parameters.
Okay,
Okay. So this process so this whole thing which we did just now, you're going to follow this whole thing again and again till some layers, right? So let's say in decoder stake, you see they're following this process 6 times, right? So same thing I'm going to send again, then again, then again, then again. So 6 times I'm going to follow the same procedure. I'll do mask multi-head attention, then I'll do mask multi-head cross attention. Then in cross attention, so how do you do is layer one of encoder is connected with layer one of decoder. Similarly, layer two of encoder is connected with layer two of decoder, right? That time. So each time they will share the information. Okay, and you have to do it for some layers. Now all of this was done so that your model will have more and more parameters. So that's right. So if you have seen the war of large language models, they always say, you know, this new model is learning parameter 1 billion learning parameter, 2 billion learning parameters. So why they are getting so many learning parameters from this architecture, right? So you can see how many learning parameters are there, right? So that's how they this learning parameter. More learning parameters means more better model. That used to be the case. Now it has changed in some few, like maybe last year only when DeepSeek came, but before it was like the bigger the model, better the uh, outcome. Okay. So any other question?
Yes, sir. In the September 2024 paper, there was one question for calculation of parameters of transformers. So that calculation is not getting correct. I mean, I tried to solve it. And similar question is there in December 2024, but there the answer which I am calculating, I'm getting it right. So will
It,
you be able to solve?
yeah. So can you share the question?
Yeah,
Okay.
sharing the
So
question.
I think there is a mistake in the previous term, in like way before this parameter calculation, but we can clarify it.
Sir, can I share my screen because it's in PDF?
Yeah, sure.
Yeah, thanks. Just a second. Yes, sir. This question.
Okay. So they are saying that input dimension is 20, then there are two heads, and the head output of each will be 10, right? So um, uh, okay. Just a second, I'll just take a photo of this and then I'll. Okay, so I'll reshare my screen and I'll show you how to.
Yes, sir.
Give me a minute. I'm just. Okay, I think my screen is visible.
Yes, sir.
Okay, so this was the question. Now, okay, so what they are doing is we have one um uh, so this is multi-head attention, right? So this one head attention calculation, let's say this is another head, and we're going to concatenate them, right? Something. So they are sending 10 size here, 10, and we are getting a 20 here. Okay. So two heads are there, and dimension of feed forward network, so which will come after this, right? So after concatenation, what we do, we pass. So we have one linear layer also, and multi-head
So head
attention.
output is that alpha into that value, right? CJ.
Sorry.
Head output dimension they are mentioning is the CJ dimension, right?
No. CJ. No. That um CJ. So sorry. So CJ and all were in the when we are doing just attention. Now we are talking about self attention, where CJ of some like that concept is not here, right?
Okay, got
It
it.
is completely different.
Okay, this is just in.
Yeah. So okay, now we are doing concatenation, and then we are passing through a FFN layer, feed forward neural network, and which is dimension of 16. That is okay. So what they mean by 16 is, let's say this hidden layer is 16. Input of that is going to be 20 only, right? Now I understand that this time we are not expanding but reducing, but that's our question is. So we'll have another of some I guess 20 only, right? So that I can get 20 output. now I have 3 decoder layers, so that is okay. 3 decoder layer is kind of okay. Uh, uh, so if I will be able to compute this one, then I can definitely multiply it with 3, and whatever output I get, that will be correct answer, right? Now this is
Sir,
octocode.
after 16, why you have put one more layer of 20?
That's how feed forward network was, right? You can see
2
this
layers.
one,
Yes.
right? This one. So this is 16, and this is again
20.
512 was it? So 20, I'm saying.
On
Okay.
20. This down one is also 20, sir.
Which
16,
one?
20. Okay.
W1. Yeah. So this, sorry, this one. So it will start with 20. Then we are saying that there should be 16 in this, and then of course I need 20, right? After I do all the computation.
Sir, what
So
is the head output 10 means?
So head output 10 is right. So okay, now we are talking about this, right? So this one head is producing of size 10 dimension. So this another will produce 10 dimension. Now if you going to concatenate this two, you'll get a 20 output, right? So that head, each head will produce
10. But
yeah,
you are
10
right at the
size,
input side, right?
or
That's
t cross 10 also you can say. So t of course will be that t cross 10, t cross 10, then you'll get finally t cross 20.
okay, sir.
So for each of them, I have to compute it. So I was just talking about one token only, but you have to compute for all the tokens. Now, assume that each decoder layer, what they are represented decoder layer, one multi-head attention. So, okay, one multi-head cross attention. Okay, so encoder decoder, something like that. So, yeah, and one feed forward and no
Multi-head
bias.
attention for encoder decoder means cross attention, right?
Yes, cross attention also you can say, right? But computation wise, nothing changes, right? We just introduce another WQKV. That's all,
Okay, sir.
right? Okay. Now let's see what will be the number of parameters in this. Okay. Now, uh, okay. So let's see first what is there in the multi-head attention of decoder. Right? So first input in that. So we have input of size 20, right? And we have to input dimension or head output dimension is 10. Never mention what is that T model. Okay, that is fine. Now let's see what is. So one is we have to compute what is WQ, and generally what we do is if we are able to compute what is WQ, we multiply it with 3 because we have WK and WV. Okay, so we by default we assume that these three have same dimension, and um, uh, uh, input dimension is 20. So okay, so my input, which is this, is 20. Now okay, I think I'll get Q here, and I'll get Q transpose K of size 10 only. So how will I get that? So if this is of size let's say my give me a minute, okay? I think it would be better if I show you the multi-head attention calculation, and in that we will do it.
So to get Q, how I did is like 10 we have size and then 2 heads. So 10 into 2, 20,
Yes.
and then multiply with the input size. So we get 400.
Mm, uh, yes. So that is correct, right? So let's say I think I have given you this, but just in case if you don't know, so what will be the um, DQ or in this we needed of 10, right? In this 10, and D model was given 20 to the question. Embedding of input was 20, right? So we'll get 200 in this case. Then similarly, we'll have WK also, which is of 200, and WV also 200, right? Now, they uh, they didn't mention WO, but WO is generally let's say 20 into, we have number of heads 2, and we take DV in this case, right? So DV is 10 only. So it's like you can take 20 only. So this is going to be 400, right? So this all are there in multi-head attention. So the summation is coming out to be 1000. So this for multi-head attention 1. Now, of course, I'll do same thing for um, same thing I have to do for cross attention, but the catch with cross attention is just remember that um, that in cross attention we don't do this multi-head. Sorry, we can do multi-head cross attention, but I think what they mean is single cross attention only. Now I'm not sure if they mean one attention head or multi-head cross attention. So depend on the question, it might change. But let's see. So I'll give you the idea how you can compute or how you can calculate the parameters. But I'll
Sir,
leave it up to you,
why we want W not calculation?
because we have two heads, right? We did the concatenation. Now this linear layer will be there. So this linear is WO, right? So these are also parameters, correct?
Linearly, that is only they are told, right? Only XMN is there.
No, FFN will be there, right? Is it? It's always going to be there. It is outside of multi-head attention. It doesn't come under multi-head attention.
Okay, so the question what I understood is there are self attention and cross attention, then directly FN.
No. It is, see, if you see multi-head cross attention, FFN is different thing, right? Now, if I show you what is multi-head, this is multi-head where concatenation is there. Linear layer is also there. Okay, so this is WO. Like here, right? So this is a multi-head attention. Now on top of that, you apply FFN layer, straightforward neural network, which has this many parameter where W1 and W2 are there. If you exclude the bias, then W1 and W2 are going to be there, right?
Okay.
Yeah. So see, the question which we are solving has, I know it is incorrect answer because this in previous term also we resolved it, but it is has different answer. Now the thing is, okay, so we are taking multi-head self attention, multi-head cross attention, and both of them are two heads, right? So the computation won't change for both of them. So what we saw is we did my MHA computation where we got 1000 parameter. Then I'll do MHA, but this time cross attention, right? So nothing changes in terms of parameters, right? I have to introduce this different WK2, WV2, WQ2, and that I'll do 2 times. And of course, I'll apply the concatenation and linear layer. So nothing changes there also. So again, I'll have 1000 of this. Now the output I'll get is of size 20. Just remember that output will never change. Whatever my input is, that is always going to be output of embedding. Now I'm applying a 16 layer FFN layer, and that 20 layer, this 20 layer, another output of this FFN, right? So how many parameters going to be there in this? So this is going to be 16 into 20 into 16. Sorry, into
20 into 6 plus
Into
yeah, sorry,
2,
sorry, sorry.
2 sir.
20 into 16
Into 2.
plus sorry
plus
plus 16
yeah.
into 20.
16 into 20.
Yeah, or I can do multiply by 2. That is also okay, right? So this 3 things I do, and yeah, nothing else, right? So this 3 components, 3 architectures are there. One is MHA, and the cross attention, and third is this. If you add all of this, you get the final number of parameters.
Sir, we have to multiply by 3, right?
Multiply with V.
3, because weight we have.
I didn't get it.
No, actually 1000 you got, right?
Yes.
So before that we have to multiply by 3 items, right? So because we
T is due to decoder, right? That's what you mean?
no weight, 3 weights we have, right? WQ.
Yeah, no, 3. All 3 have concluded. So WK was or WQ, WK and WV were 200 parameters were there in that. Right. For example, let's say my embedding is of size 20, and then I have this
That is
W.
for each one, right? So we have to add everything, right? So it will be 600.
Yeah,
right?
so if I add all of them, I'll get 600.
Yeah.
Now I'm getting 400 from WO. This is WO, where I'm getting 400. That's why I summed it up and said 1000.
So we need to we have the embedding input also, right? That also we have to add, right? So 200 will not come.
Which embedding?
So actually from self attention we are getting WQ, right, to the second cross attention layer.
Yes.
So there should not be add 200 to the 400.
That is also done in this cross attention, right? So see, what I'm saying is you compute MHA, multi-head attention normally, right? So this is normal attention, and then you compute MHA with cross attention.
Yeah. First one
Right.
I got 600. That is.
Yeah. So now, is there any difference between these two in terms of architecture? Is there anything like here? See, 2 things: key and value are coming from encoder, right?
Okay.
And then this is coming from decoder. Query.
That is a self attention.
Yes. Now here, what I'm doing, I'm getting K, V, and Q. I'm getting from input itself, right? So now I'll have some embedding, and input will produce this. So parameter wise, nothing is changing in this or this. So if you have this parameter,
600, right? That's what I was saying.
Yeah, you can add both of them, right? Same thing, right? It's just replica of MHA.
But you wrote 1000, but it should be 1200, right? That's what confused me.
No. So what I'm saying is WK is of 200, WV is 200, WQ is also 200. Okay. Now, if I sum all of this, that is 600.
Yeah.
Correct. Now I'm saying WO is of 400. So I'm saying total is 1000. So this is the whole thing is complete, right?
So one
1000.
layer 1000 you are getting.
Yeah, 1 layer 1000 in MHA only. Now same thing is there in this, say same computation of this, and I'm saying 1000 of this. Now I'll apply FFN layer. So FFN will be this 20 cross 16, 16 cross 20, right?
Okay, like that.
Yeah, and now all of this computation, which is 2000 plus whatever is 20 cross 16 is 32
640,
and
640.
right? So 0,
Yeah.
4, 6, 2.
20 is
Now,
there, right? Output.
20, yes, 20 is the size of a yes, that is correct. So 2640 is the number of parameters and 1 layer of decoder. Now we have such 3 decoder layers. So that's why I have to multiply with 3 of this. And this is going to be the final output. And this answer is incorrect. I know that. But this is how you compute it.
So W0 also we have to calculate.
Yes, you have to include that also.
Sir, input and output size is same 20. You are not adding 20, right, sir?
Why should I add 20?
Output of the network is 20.
Yes, that is just an output dimension, right? It is not parameter.
Okay, sir.
Sir, I think we did not consider number of heads.
No, we considered, right? So give me a minute.
So we didn't do multiply by 2, sir.
Yeah, that is correct. We didn't do, right? So if we do that, that will come here, right? So this 600 into 2, which will be 1200 plus 400. So okay, so now calculation changes. So 1200 coming from WQ or QKV, I'll just write that, and 400 is coming from O, okay, WO. So this two things for one head. Now multiplied all of them by 2 also,
Yeah,
right?
yes, sir. So got it, sir. Got it. I mean, yeah, can
Yeah,
manage.
so this is 600, 1600. Again, I'll have 1600 for cross attention, and then finally that is not going to change. 640, right? So 4 here and 18, and this is 3. So 3840. That is answer for one decoder layer. One layer, I guess that's what they. No, that is not the answer, but okay, this is the answer for one layer. Now we have to multiply with 3. Okay.
Yes, sir. Got it.
Okay.
Sir, you used one PDF now, sir. Where is that PDF, sir?
It
The
is in the
calculation
group.
was.
It is in the group, right? I shared it. You can search multi-head attention,
Okay.
something like this in the group, the G space. You'll get it.
Okay, sir.
Okay. Okay.
W0 will be for both the pros and the mask retention, right?
Yes, it will be there for both. Yes. I mean
Okay, so
different WO.
yeah, that also we have to add for the number of parameters.
Yes. Yes. Okay. Anything else?
Sir, BTT, can you just explain with one example?
Sorry.
Back propagation through time.
That example, Karthik.
Which one,
Are you
man?
there? Is there any way you can explain back propagation through time?
For what? For you through time, huh?
Yeah,
through time.
the RNN back propagation.
Yeah, so that is a big one, man. So that will take
Okay.
time. So what I have done in the live session, right? Last RNN live session, that is simple enough, right? That much, if you know, it is good enough.
Okay, in exams also that much.
So I have done one simple example, right? Where you have all our scalars. So that
up to two I am able to understand. After that, it's confusing for me.
That is good enough. See, in reality, all these things happen through what are called computational graphs. So the way it happens is kind of totally automated. So there's a concept called automatic differentiation, right? Where whatever function you give, as long as it's differentiable, the system will know how to program, right? PyTorch or whatever computer application you use, that will figure out how to find the derivative. So you need to have a general idea of how back propagation through time works. For that, those 2 time steps are good enough.
Okay.
Yeah, so one point, those of you who seem to have watched last term's transformer video, right? The notation there I use is different. This QK transpose is what I use. So please don't use that for the exam. Whatever Manoj shared, right? Q transpose K. So always stick to this terms. So Q transpose K is there in the video lecture also, right? So please stick.
Rest all are same, right? Rest all are same equations, derivations, all those things same, sir. Only Q transpose is different.
Yeah. So that is just that n cross d. So how you choose to represent your data matrix, right? So the way I had chosen was n cross. My input was n cross d.
N cross d.
Yeah, but please use this whatever Manoj shared, right? Q transpose K. Use that itself. Don't use the previous one.
Yeah.
Okay,
So this is same as the how sir has done, right? So
Yeah.
the
Whatever
post slider. Yeah. So So whatever is in the course content, you have to go follow
So
that
Manoj, that
notation.
alone, can you add it in the group? Because I had used a different convention last term, and some of them I may have watched that.
Yeah, sure. I'll add that.
So any important topics to be asked from 1 to 8? Okay.
Sorry, any important?
Important aspects to be taken from 1 to 8.
I can't think of important aspects. I think important aspects. Oh, you have done quiz 1, quiz 2, right? So you kind of know what questions we ask. So basics, if you're strong with your fundamentals, that should be enough, right? How to, yeah. So all your optimizers, you must be knowing how back propagation works. You must know how CNN filter sizes you have to calculate. All that you have to know. And the first week, how perceptron works, how the perceptron update rule is functioning, MP neurons. What else is there? Feed forward networks, parameter calculation. Those are the usual things, right? So that if you know those things, I think you're.
Okay, sir.
Sir, we have to remember the equations of LSTM, GRU. That is sigmoid, UX, XT.
RNN and LSTM you should know. GRU, I think you can skip.
Okay, sir.
Sir, last time paper was little lengthy date, so is it like similar to that or?
Same like quiz 2, sir. We will panic.
Yeah.
I don't know. I think this time it is not lengthy. It is more of. No, I think this time it is not lengthy. If we know, if we understand correctly, I think it is 90 minutes you can do.
And weightage will be more of 9 to 12, right?
Last 4 weeks, right? Or last 4 weeks mainly. I mean,
Okay.
mainly means what? More than 50% last 4 weeks.
Yeah, got it.
Yeah. So you should not come back and tell us it was more than 50%. What we have mentioned is at least 50%, right? So it could be more, it could be, it depends, right? So we can only tell you that more than half the paper will be from last 4 weeks.
Thank you, sir. Thank you for the wonderful session.
Okay, so yeah, thanks. We can close, right, Manoj?
Yes, sure. We can close.
Okay. Yeah, it's closed.
Yeah. Okay. Best of luck, everyone.
Thank you, sir.